everyone, and welcome to our module on climate change. This is a really exciting topic. It's hot in the news. It's seen as controversial, but that's really only among the news, politicians, but among the scientific community, climate change is not seen as controversial at all. And in fact, it's seen as an issue similar to the ozone hole, that really it is required for a global community to come and make changes to prevent catastrophe. So let's go ahead and get started. All right, before we get started, I want to make it very clear. The greenhouse effect is not climate change. The greenhouse effect is natural and vital to life on Earth. So basically, what we have with the greenhouse effect is you have sunlight goes through and hits the Earth. It passes through the atmosphere, and you have UV rays, you have infrared, you have visible light. All of that goes and hits the Earth. And this is similar to a car. So you have your car here, and if you were to make the analogy that your window shield is your atmosphere, okay? So the sunlight goes and through the window shield and hits the inside of the car. And what happens to the inside of the car is it starts to warm up. And what happens, the seats get hot, the steering wheel gets hot, the inside of the car gets hot. And that heat actually is no longer UV light, it's no longer visible light. It actually now is infrared radiation coming out of the seat or out of the steering wheel, whatever is warmed up. And that energy can't escape the window. It's a different type of energy, it can't escape the window. And so all that heat and that heat gets trapped inside the car, and the car keeps warming up and warming up and warming up. And so that's why even on a cold winter day, the inside of the car is hot because of that effect. And the greenhouse is the same way. This greenhouse effect, our atmosphere, so this light, this energy can pass through the atmosphere, and it goes and it warms up the surface of the Earth. So once the surface of the Earth is warmed up, it starts to radiate back out infrared radiation. And some of it, yes, can escape. Otherwise, we'd have like a super hot planet that we couldn't live on. Okay, some of it does radiate back out. But a lot of it, just like that car window, actually gets absorbed and re-emitted back to the surface of the Earth. And this re-emission back to the surface of the Earth is what makes our Earth habitable. Without that, our Earth would be 33 degrees cooler. All right, so let me just emphasize that. As a result, the Earth's surface is 33 degrees Celsius warmer than it would be without an atmosphere. So the atmosphere is more, it's kind of like a blanket. It keeps us warm, keeps our planet, habitable. One thing I want you to notice, though, is that we do not keep all of that energy inside our atmosphere. Eventually, it does get emitted back out. And this is what we call the Earth's energy balance. So the sunlight sends out energy to the Earth, and let's say it's 100 energy, and it gets absorbed by the Earth. Okay, some gets absorbed by the atmosphere. Now, if you look at the numbers of everything being emitted back out into space, if you calculate all these numbers, everything from the amount being emitted to the atmosphere, from the surface, reflected from the surface, reflected from the atmosphere, it would equal 100. So amount of energy in equals the amount of energy out. Okay, now that we have that squared away, I want to start talking to you about carbon dioxide. Now, there was a scientist in the 1950s that decided he wanted to measure baseline carbon dioxide levels, and he decided the best place to do that would be in Hawaii, since it's far from factories and and far from lots of cars. And he started taking data, and what he found is that over time our carbon dioxide levels have been rising, which was surprising. You wouldn't expect that. So what you see with these zigzag lines, this is actually just a seasonal variation. Here's just a close-up of that so you can just identify that that's just a seasonal variation. And his data from Hawaii was actually backed up further by ice core samples done in Antarctica. So if you look at this first image on the left-hand side, this is a glacier in Antarctica. All of these rings just indicate years, like you do the rings on a tree, indicating how old a tree is. So you can actually see how old these glaciers are based on the rings. And all those rings indicate just you have times where you're getting snow and times where the snow is melting. So the little ring is like melting ice. So summer and winter. And here's a picture of the ice core taken from the glaciers. And what's interesting about this ice core is that within it are these microscopic air bubbles. It's really fascinating, actually, these microscopic air bubbles. So you can see what the atmosphere or the air was like a long time ago. Now here is a comparison chart between the data from Hawaii, the Sipple ice core, and the Law Dome ice core in Antarctica. And here again on the y-axis is your CO2 concentrations in parts per million. And here is the year from 1000 to 2000. Notice that the ice core data shows that the carbon dioxide levels have not changed dramatically within this time frame. They're pretty much level, the same. And then you hit about the 1800s when the carbon dioxide starts to dramatically increase. There was another ice core data from the Vostok team, and they have the data going back 400,000 years, and this is an image. This is a graph of that. And just to know, other ice core data even can go back further. All right, so here's thousands of years ago, so this would be 400,000 years. Again, CO2 concentration on the y-axis. So you can see that there are variations in carbon dioxide in the hundreds of thousands of years. And these are just considered ice age cycles. So you have periods of warming and periods of cooling in our history. And just to let you know, we are actually supposed to be entering where we are in history. We are supposed to be entering an ice age soon. As you can see, we're towards the bottom of this graph. Based on the previous data historically, you would expect us to be in an ice age soon. And it's not exactly sure when, but soon. But what we are seeing is that from the ice core data that the carbon dioxide levels have increased dramatically. And actually it's 100 parts per million if you compare it to any other part, and basically any other time in the last million years, we have 100 parts per million higher concentration of carbon dioxide. And if you zoom in on the map or the graph, you will see here that actually the carbon dioxide levels again started to rise pretty much in the 1800s. What was so special about the 1800s? What happened? The Industrial Revolution. We started burning fossil fuels. Now, if you take that ice core sample, you can actually also get temperature information. And the way they are able to get temperature information is they compare isotopes of hydrogen in the water. So the water is frozen, and they can look at the isotope of the hydrogen in the water. So you have heavier water, or heavier, it's just they have a heavier hydrogen, has more neutrons. So you have like H2 versus H1, which would be your normal hydrogen. So they compare these two ratios of isotopes, and depending on the ratios, you can tell what the temperature is in our world. And what they have found is that actually the carbon dioxide, which is your blue line here, is closely correlated with the temperature, which is your red line here. So as carbon dioxide levels drop, the temperature drops. As carbon dioxide levels increase, temperature increases. The interesting thing to note is that if you look at this side of the graph where we are currently, you would expect actually our temperatures to be higher, right? The carbon dioxide level is higher and our temperatures aren't. And the scientists don't exactly know why. They believe that it might have something to do with our oceans. Our oceans are absorbing a lot of the carbon dioxide and helping counterbalance that effect a little bit, but it's not really known for sure. So one thing I want to point out to you is that this global temperature trend is global, meaning it's an average overall temperature trend. If you were to compare, actually look at a graph of the world, this is from National Geographic, it's a really nice one. If you look at the temperatures here in the color, dark red is plus 15 degrees hotter, and you keep going down to lighter reds until finally you get to white, which is no change, and blue is cooler. Notice that the red area here on the graph, the most hottest area, is our Arctic region of the world. There are parts that are actually cooler, but for the most part, most of the world has increased in temperature by at least a degree or so. And parts of the Arctic have warmed as much as 15 degrees since 1960. I'm not talking about 1800, since 1960. It's pretty scary. And what you're looking here, this beautiful picture from National Geographic, is the glacier melting. All this water just flowing into the ocean. And we are already seeing the consequences of this. If you look at this graph on the left-hand side, centimeters on the left, years on the X, from 1800 to even just 1980, we have already seen the sea level increase in many parts, right? This is annual average sea level by about, what does that look like, 6 centimeters? Okay, and then there's different scenarios depending on what happens to our planet, how bad global warming gets. We have different scenarios of how bad the sea levels will rise. I have a better graph for that one in the next slide. But there are two main reasons why global warming is rising the sea levels, and I want you to think about what are they. Number one, for sure the melting ice from the land, and two, water expands with heat. That's simple. They'll have hotter oceans, so you're going to have water molecules further and further apart, which means you're going to have more a higher sea level. And so here's the graph I want to show you about the different projections of scientists. You have the low projection, like, oh, we're not going to increase the sea level too bad, it's not going to get too, like maybe up to 10 centimeters, not too bad. Right, then you have the median projection based on, you know, how bad everything gets. This would be if we were to increase to about 50 centimeters, that would be more than a third of US wetlands would be underwater. And if we get to the high projection of how bad things could get, we would be around 80, even to 100. Some scientists even go to 100 centimeters. That means Shanghai, New Orleans, and other low-lying cities would be underwater. And I have some news for you. New Orleans is already below sea level now. And that's happened after Hurricane Katrina. Okay, so this graphic is from 2005. It's kind of outdated here. It's already below sea level as of now, and it's only kept dry through the levees. And so not only are we seeing this effect in the Arctic with the melting ice, we actually see it in our own state, California. Here's the Sierra Nevada in March 29, 2010. Here's the Sierra Nevada in March 29, 2015. You notice that the snow here, we have a good amount of snow here in 2010. In 2015, there's just 5% of its historical average. We count on the snow for our rivers, right? During this, when it's not raining, where's that water flowing from? In the river and the streams, it's from melting ice and snow in the mountains, and it just trickles down into the rivers and keeps the water flowing. We count on that ice for our snow, for our drinking water, for our irrigation water for crops. So this is a major issue for California. And not only is it a major issue for California, it's a major issue worldwide. We are seeing freshwater stress globally. Okay, so especially in areas that are in the orange and yellow on this map are areas that are experiencing water withdrawal more than 40%. And in 2025, we're even looking at a larger projected area. And the simple reason for freshwater stress is it's hotter, so we have more evaporation from lakes and rivers, which means more humidity, lower quality water. That also means it's hotter, so you have less snow storage. You can get contamination of your groundwater, or it's also called aquifers, from the ocean levels rising, meaning you get salt into your fresh water, and more droughts, and that also means more flooding too. All right, well, that is it for our introduction on global warming. So I hope that gives you a good idea of the background of what carbon dioxide is. In the next lectures, we will talk about more of the scientific background that you need to know to understand global warming, and we'll talk about the human aspect to it as well. All right, I will see you next time. Bye-bye.